what I want to do right now, guys, is look at, I want to share the screen and just sort of pick up where I left off yesterday. And then I'm going to allow you to ask questions about the homework, because there's one problem that I messed up something right at the end of the class because I got in a hurry. Shouldn't have done that. And then there's one other thing I want to review with you about what I did yesterday. So let me share the screen on the iPad with you, and we'll get started on that. And then I'll take homework questions, okay, if you have any. Okay, got this, hopefully. I don't want to see my personal ID again. That's fine, whatever. All right, so let's go here. Okay, everybody see that? Are we okay with that? Okay, yesterday, what we learned to do was find out where a function was increasing and decreasing. And what it consisted of was taking the derivative. By the way, most of your derivatives were fine on the test. A few errors, maybe not using the quotient rule when you should have, and few errors with powers and things, but those look pretty good. What you do to find out where a function is increasing and decreasing is look at the derivative. So yesterday I started doing this example, and I will go through the steps again. It says find the derivative, and when we did that, we got 3x squared minus 3x, and then we had to find what were called the critical numbers. And in order to do that, we typically want to factor the thing. Now, the critical numbers are just points that make the derivative 0, because that's where things go from being positive to negative. And as we learned yesterday, when things are positive, the function's increasing. When things are negative, the function's decreasing. So I've sort of indicated that here. I found these critical numbers. That's what those two things are right there. By the way, has anybody watched any of the videos? Are you able to get to the video? Okay, yeah. Let's see. Okay, good. Because you can watch it over again, but I messed this one up yesterday, so whatever. This is the good one. So the critical numbers were 0 and 3. I put them on the number line, and then I test a point in each interval, and I test that in the derivative to find out whether it's positive or negative. Not in the beginning function. In the beginning function, that's where we get points. Okay? Here's where we find out increasing and decreasing. So I put 0 and 3 on there. Maybe I picked a test point of 4. 3 times 4 is positive, 4 minus 3 is positive. When you multiply positives, you get a positive. I did that in every section. Where I got a positive, I got increasing. Where I got a negative in between, I got decreasing. Now, what I did wrong yesterday when I got in a hurry was looking at the graph. I plotted a point wrong, and things were going haywire. And so I just said, forget it, I don't want to waste my time on it now. So the critical numbers were 0 and 3. If you want actual points to put on the graph, what we got to do, of course, is just take those points 0 and 3 and plug them into the original function. Clearly, when you plug 0 into this function right here, you get 0. And if you plug 3 in, you end up with 27 halves. So you have your calculator close by, but the 2 points that I got here were 0, 0, and 3 and 27 halves. And for some unknown reason, I plotted 3 and 27 halves down here. Well, I should know better than that. That's positive. Positive is going to be in the first quadrant, not the fourth quadrant. So I have no idea what I was thinking yesterday. But anyway, it goes through 0, 0. So I've got that point. 27 halves is about 13 and a half. You can make a scale here if you want to. Suppose it's in 5s, and that's 5, 10, 15. That would be about right there. I can get it to mark. Okay, there we go. That's that point 3, 27 halves. Now look at your sign chart and realize that from minus infinity, and remember minus infinity is over here, up to that point, up to 0, we've got an increasing function, and I'm messing it up again. What I'm trying to figure out what. Let's see. Now test my signs right here. I got that and that. That's negative 0, 0 is on there, and 3, 27 halves is on there. So I've got increasing, and to that point. All right. So it may be increasing Gosh, I just looked at this and now I'm getting messed up again. 0, 3, 27 halves. It's not that hard. Anybody see what I'm doing wrong here? So increasing up to that point. So technically it should look like that, okay? It's supposed to be decreasing between 0 and 3. So it looks, it should look something like that. And then from beginning at 3, whatever the point is at 3, it should go up again. So I've got increasing, decreasing, and increasing. Again, I must be plugging in the, anybody see anything wrong with that?
Have you graphed it on the calculator?
Yeah, I could. The whole point here is really not to graph it on the calculator, but if I graph it on the calculator, I could, yeah, let's just do that, guys. And let me see if I don't know what I'm doing wrong, because that should not, that's
it looks like that it's going up and then it's decreasing below the
it does. It does, but the reason I don't think it can do that is because what I plugged the function in, I got 27 halves when I got 3. Now the question is, did I plug that in wrong? So if
then it goes back up to the 3.
Say that again?
It goes back up to the 3 after it goes down.
Okay, but it should be, and according to something I'm telling you today, this should be right there at 0. There should be a peak, and if I plug in the point 0, I get 0. So there should be a peak there. And you're right, it should go back down. All right, let's do that. It should go back down until I get to some point at 3, right there. I'm going to erase something here. This might be what I did wrong. A point right there, and then when it gets to 3, it should start it should start increasing again. So it should look something like that, and then it should look something like that. Okay, whatever that point is. The thing that was throwing me off is I was getting 27 halves. I thought I would get minus 27 halves. Let me put it in the calculator. Let's see what we get. And if you keep your calculators with you here, guys, we'll need them just to sort of check things. But again, the idea here is to graph it without knowing a whole lot of points. So I'm going to put in, let's go back to the original function here. The original function was x cubed. All right, so I got x cubed. And I'm going to come back down and put in minus 3 halves x squared. That's minus 1.5. Minus 1.5 and x squared. Okay, so x squared. And I don't know what my window is. I'm going to check my window. Oh, the window's a little bit weird. I'm going to go, since I've got 0 and 3 on there, I think I'll just do minus 5 to 5 for my window. Okay, so minus 5 for the x-min. I've also hadn't quite figured out how to get this up on the screen, but I'll sort of talk through it here. I'm going to set them from minus 5 to minus 5. That's x-min and x-max. Minus 5 to 5. And then graph it. Yeah, it goes below. Have I got a wrong critical number? It has that shape that I just drew there. All right, it has exactly that shape. 3 squared would be 9. That's 27 halves. That's 27 minus 27 halves. All right. Definitely goes below. If I'd taken the derivative right, 3x squared minus 3x, derivative's right. I got the right critical numbers. That's about what it should look like. I'm getting a wrong value for this thing right here. I'll look at it again. But let me go to another one. This is what I did yesterday. Let me go to another one. So that's the thing we do. We find the critical numbers. We find out where it's increasing, where it's decreasing. Now, let me show you something on right here that sort of talks about what somebody just said about, well, put it on the calculator. The question is, maybe I want to draw it without knowing what it looks like on the calculator. And that's the power of this, to figure that out for a function when you can decide where it's increasing and decreasing without maybe looking at the picture. So let me show you what I've got here, guys, and then we'll talk about what it means, and that'll review us on what we learned yesterday. If you look at this, it says draw a graph with the following information. F of minus 1 equals 3. F of 2 equals 8. F prime of x is less than 0, from minus infinity to minus 1 and 2 to infinity. Now, f prime of x is greater than 0 between -1 and 2. It's asking me to draw a graph of this, and I don't even have anything on the graph, except that I have a couple of things about it. What is this telling me right here? What does f of -1 equal 3 tell me? Anybody unmute or whatever you need to do. What is that giving me? Remember now, that's a y value. So what is it giving me there? If it says f of -1 is 3. Say it again.
Isn't that a point?
It is a point. It is a point. What point is it, guys?
-1, 3.
Yeah, -1, 3. Okay, wait a minute. I just hit something weird on my screen. What are y'all looking at here? Anyway, I don't want to go there. Let me go back. There we go. All right. So it's -1, 3. Back here. So they're giving me a point. So I do have a little something to hang on, and I'll put that on the graph in a minute. So tell me what that one's saying.
2, 8.
2, 8. It says when I plug 2 into the function, we get 8. So we'll be leaning heavily on the functional notation here, guys. Now, let's look at this thing right here. What did f prime of x being negative tell you about the function? If the derivative was negative, what did that tell you? Decreasing or increasing?
The slope is going to be negative.
The slope's going to be negative. Therefore, the function is decreasing. Yeah. On that question on the test, everybody did really well because I asked you in one place, were the profits increasing or decreasing, and you got a negative derivative. That meant the profits were decreasing, all right? Or whichever it was. Positive, it was increasing. So in between, if I draw a line down here now, I can kind of get a handle on what's happening. So from -infinity to -1, and then from 2 to infinity, it says it's less than 0. All right, f prime of x is less than 0. That says it is decreasing here because we get a negative derivative. To the right of 2, we also get a negative derivative, so it says it's decreasing there. Well, I'm not doing, the pen and I are not getting along well today. All right, anyway, so it's going down, it's going down. Now, between -1 and 2, it says the derivative is positive. Well, if the derivative is positive, we know the thing is increasing, okay? So I'm gonna have increasing and a positive derivative, so it's going up. So here it's going up on that side of 2, anywhere in between -1 and 2, it's going up, okay? So what are -1 and 2? They appear to be what, guys? Where do things change? What did we call them? What name did we give those places where where the derivative was 0, basically? Anybody? Those are what we call critical numbers, okay? So those are the things we would get from the derivative. We don't have the function here, but that's what they're doing. Those are the critical numbers. Okay, so what I've got is all of this information about decreasing, increasing, and I want to try to graph it. Now, here's what I'm going to do to graph it. First thing I'm going to do is put my points on. So -1 and 3, I'll put that one on first. Okay, -1 and 3 is up here. Okay, I'll label it. And then the other point that we found was 2, 8. So right here, 1, 2, and somewhere up here. So 2, 8. Okay. Now, that's all I really have to hang on to. I don't have any function to plug things into, but I do know how the function behaves. And what it says here, if you look at my chart right up here to the left of -1, and there's -1 right there. What's it doing to the left of -1, guys? Again, what's it doing there?
Decreasing.
It's decreasing. So when I draw that, I'm going to go down to here. It's decreasing until it gets to that point. What did it do in between -1 and 2?
Increasing.
It increased until it got to 2. So here's 2 right here, and there's the point with 2. So it goes up, it increases there. And then what does it do after that?
Decreases.
It decreases, okay? So that's what it looks like. And I plotted, I was given 2 points and I know roughly what that graph looks like. Does that help, guys? I think I might have, you have a quiz due on Monday. And that one, it's just and it's on Moodle. So, and I want you to scan it to me like you usually do. I'll get something figured out over the weekend when I have more than 30 seconds to look at something. But when you look at that, it'll be a function. You want to find out where it's increasing, decreasing, what the critical numbers are, of course, starting with the derivative. And then I'm going to get you to just draw a sample picture of it based on your increasing, decreasing, your critical numbers. Now, remember, when you find the critical numbers like -1 and 2, you still have to find the y value that goes with it. So you'll have to go up to the original function to do that. Don't put it back in the derivative because it'll just make it 0. Go back to the original function to get those points. Okay. All right, guys. Did anybody have any issues with the homework?
I have a question.
Okay.
On page 175, number 7, where it's just find the critical numbers.
Okay.
It just threw me off because it was like x4 plus 4x3. They were just they were bigger.
Okay. All right, that's a good one. So you said it's number 7? 7?
Yeah.
Okay. So let's look at that. So guys, this is number, oops, this is number 7. Get up a little higher here. Okay. On page 175, is that the one? Is this Haley that asked me that question?
Yeah.
Yeah, okay. So it's x to the 4 plus 4x cubed plus 8?
Yes.
Okay. X to the 4th plus 4x cubed plus 8. All right. So what I want to do is it says find the critical numbers of the function. And that's pretty much all it says. It doesn't tell us to go any further. We could go further. We could find increasing and decreasing. I may do that. But all it says is find the critical numbers. So I'm going to take a derivative, which would be 4x cubed plus 12x squared. Just using the power rule on those things. So that's 4x cubed plus 12x squared. Critical numbers are where this thing is equal to 0. So I need to factor that. So somebody, first rule of factoring, get out any common factors. What's common here, guys? What can I pull out? Anybody?
4x squared.
I can pull a 4 out of the 4 and 12 and an x squared out of both of them. So 4x squared times, and I'll be left with x plus 3, it looks like. Okay, x plus 3. So now, maybe the hang up is this, guys. You want to find out where that's 0. It's clearly 0 where if either one of these terms, this one or this one, are 0, you're going to get 0 because 0 times anything else is 0. So one of them that's fairly obvious is -3 because it makes that one right there 0. Now, I'm not particularly worried about this square right here because if whatever makes x 0, we know 0 squared would also be 0. So what value makes this 0 here, guys? The 4 is just 4. That's not going to change. What would make x squared equal to 0?
0.
Just x equals 0. It doesn't matter if that was to the 100th power, guys. If you put in 0 here, it's going to be 0. Now, I am going to go a little further with this problem because it'll help us, I think, with the rest of the homework. The other thing we learned how to do was find this increasing, decreasing. So once we do that, we put these critical numbers on this line. And so let me show you sort of what happens here. Make sure they're on there in the right order. -3 is to the left of 0. I'll go back to this factored form of the derivative. And I'll pick a test point in each one of these sections. So suppose in this section I pick 2. 2 plus 3 is going to be 5. 2 squared is positive. All this is positive times a positive will give you a positive. So what we would know there is that this function is increasing to the right of 0. Let's look at a test point in here. If I plugged in -1, -1 plus 3 is positive, and -1 squared is positive. 4 is going to be positive. So I got a bunch of positives here. That means that's going to be positive. So that means it's increasing there. Now, guys, some of the ones I had, it made you think maybe that it always alternates, but it doesn't, because this power right here makes things positive in many cases. So if I look at -4 squared is still going to be positive, but what's -4 plus 3 going to be? Positive or negative?
-1.
-1, yeah. And I don't particularly care what it is, but I do care that it's negative. So that's a positive times a negative, so I'll have a negative. And that will make it be decreasing, okay? Now, if I wanted to draw a graph of this thing without the calculator, then I would want to find out what the point was. I need a couple of points to hang my graph on. Okay, well, that's all the book said to do, really. I did more. Haley, what was the problem? Do you see what you see what
Yeah.
the issue was? Okay. Was it the square?
It was just the like the x to the 4th and then the x to the 3rd, since they were bigger. I guess it just had to. I forgot.
Yeah. Once you you couldn't have solved that if you didn't take the derivative, because you wouldn't know how to find the zeros of that function. Okay.
Yeah.
So that was probably the problem. So on this one, if I said I want to find f of -3, I need a point to hang this on. So I'm going to go to the original, and I'm going to get my calculator here, and I'm going to put in -3 to the 4th, -3 to the 4th, which I know is actually 81, and then +4 times -27, and +8. And what I get there is -19. Okay, it's easy. What do I get if I plug in 0, guys? What's f of 0? Now, remember, I'm plugging it into the original. What's f of 0? Anybody? Plug in 0 here, you get 0. Plug in 0 there, you get 0. And then you do what? Add 8, and you should get just 8. So if I were looking at graphing this problem, without looking at the calculator, although I could if I wanted to, I would do this. I'd plot my -3, -19, my scale. I'm just sort of making my own scale here, guys. -3, -19. And I'd plot 0, 8, which would be up here somewhere. 0, 8. Ignore that blue line down there. That's what's happening there. So notice what, I'm going to try to draw it. It says that to the left of -3, this thing is decreasing. So there's -3. That means the graph is going to come down until it gets to where x is -3. So the first part of this has got to look like that. Okay. What does it do between -3 and getting to this point? Well, it's increasing, which we know means going up. So that means it's increasing. Now, because I kind of know what's going to happen, and you'll know eventually what's going to happen, that was a place where the derivative was 0. So there should be a horizontal tangent line here, but they don't always happen at peaks and valleys, because I know here that says from 0 to infinity, it does what? What is it? Is it increasing or decreasing? Well, it keeps on going up, doesn't it? So what happens is that it just keeps on going up. Why this is a critical number is because it flattened out just for a second. It doesn't look too good there, but it flattened out just for an instant and then went on back up. So a critical number doesn't have to be a peak or a valley. It can be one of these kind of instantaneous places where it flattens out and then keeps going up or down, whatever. Okay, that's what we did yesterday. That's basically all we did yesterday. Your book only asks you to find the critical numbers there, because obviously if you can't find the critical numbers, you got an issue with the rest of it. Okay. Other questions on this one or the homework?
I have a question for the homework,
Okay.
9 and 10.
Okay, 9 and 10. All right.
We didn't have to do 9.
Say that again?
I don't think we had to do 9.
I might have left out 9, but I think, did I put 10 in there?
Yes.
Okay, let's do 10. Actually, 9 is a little bit weird. Because of that square root there, the domain would only be between to the right of 2 and to the left of -2. So let me just do 10, okay? There was a reason I didn't put that one in there. We may come back to something like that, but we'll just do it. Do the other one for now. All right, let's look at 10. Okay, I'm gonna start to ask you a couple things that we should always know here. 10 is x over x squared plus 16. Now, the first question I want to ask you on every one of these things is, what's the domain of this function? Now remember, domain is the set of all possible values for x. What you got to worry about are even radicals, which I don't have here, or where the denominator is 0.
So x cannot equal 4 and x cannot equal -4?
You know what? If x equaled 4 and I squared it, I'd get 16 plus 16 would be 32. If it were -4, I'd also get 16 plus 16 is 32. This is not the difference of two squares. If, Haley, I think that was you. If this were a minus, those would work. But you know what? This one's never going to be 0. Look at it. The least x squared can be is 0 or positive. And when you add 16 onto it, you get something bigger than 16. It's never going to be 0. Look at what happens when I try to solve it for that. So maybe that'll help see that it isn't. If I said, okay, I know that x squared plus 16, I would like to know where it's 0. So if you moved the 16 over to the other side, already you see something that's wrong with this. There's nowhere x squared is going to be -16, is there? Because x squared is always what kind of number? Well, it's always a positive number, isn't it? So if you were to try to solve for x there, you get the square root of -16, another problem, because we don't know anything squared that's -16. So guys, there's no problem here with that denominator. It's never going to be 0. It is never going to be 0. Now, if it were a negative, I will warn you, you're absolutely right, and you had factored it. Trick here is you can't factor the sum of squares. Then the answer would have been 4 and -4. But right now, we got a domain of -infinity to infinity. Okay? Now, the next thing I want to do is take the derivative and find the critical numbers. Okay? What kind of rule am I going to use on that to take the derivative, guys?
The quotient rule?
Yeah, quotient rule. The one that says bottom times the derivative of the top minus top times the derivative of the bottom. Now, this is the one derivative that some people got wrong because they just differentiated the top and then did the bottom. The quotient rule says you got to take bottom, x squared plus 16 times the derivative of the top, which is 1, minus the top times the derivative of the bottom. And what's the derivative of the bottom there, guys?
2x.
2x. And then what did we do in the quotient rule? We put it over the whole denominator squared, didn't we? So x squared plus 16 squared. Now, this is a good question. I think that was Stephanie that asked me this one. This is a good question because that's not as easy as the ones I've been doing, okay? You got to simplify this a little bit before you can tell anything. And the way I'm going to do it is just multiply out all this stuff in the top right here. So that'll be x squared plus 16 minus 2x squared. So multiplying out that and multiplying out that. And put it over the denominator again. And this is where you got to depend on your algebra skills here. I'm going to go up a little further. This will simplify a little further because you can combine x squared and minus 2x squared. What is x squared minus 2x squared? I'm going to combine this and this. What is that?
Negative x squared.
Negative x squared.
It's negative x squared? Yeah. So I get 16 minus x squared over x squared plus 16 squared. Now, let's review what critical numbers are. They're where the derivative is 0. Now, if the only way a fraction can be legally 0 is if the numerator is 0. Look at this numerator. Will that numerator factor right there? Be careful. What's out front? You got 16 out front. Will it factor, guys? The difference of two squares.
Yes, it will.
Yes, it will. 4 minus x.
4 plus x.
4 plus x. Good. So what would make those two things 0? What would make this first one 0 there, guys?
4 and negative 4.
4 for the first one, negative 4 for the next one. Those are the critical numbers. You want to find out increasing and decreasing, you put them on the number line and do what we did.
So you only need the numerator to find the critical numbers?
Yeah, Haley, that's the, well, if the function is defined everywhere, yeah, in this case, the only way this fraction can legally be 0 is if the numerator is 0. But let me show you one other thing. Suppose I had y equal x to the 2/3. The domain of that is minus infinity to infinity. So that exists at every point. If you look at the derivative, it's going to be 2/3 x to the minus 1/3, because if you take away 1 from 2/3, you get minus 1/3. If you rewrite it, it's 2 over x to the 1/3, which is 3rd, which is 2 over 3 times the cube root of x. Now, critical numbers can happen in one of two places. They can happen when the numerator is 0, or they can happen when the denominator is 0, assuming the function exists where the denominator is 0. This function, this critical number, there is a critical number of 0 here. Okay? However, it's only a critical number because the derivative doesn't exist there. The function does exist there. And I'm going to tell you that this one right here, if you got a derivative not existing, tell me what kind of places where a derivative doesn't exist. What's one of the main places we talked about where a derivative didn't exist?
Sharp point.
Sharp points, exactly. So look at this one a minute.
So did you get x equals 0 because 2 doesn't equal 0?
No. I got x equals 0 because it made the denominator 0. This is about the derivative being defined there. The derivative is, or undefined. The derivative is undefined at 0. But if the function is defined there, then you might have you will have a critical number there. So let me show you what happens. Get rid of that. And so what happens in this problem is this. The function exists everywhere. If you were to put this on your calculator, you would get something that looked like that. At that very point 0 is a critical number. The function exists there, but the derivative doesn't. So critical numbers can be at two places. Let me write it down for you. They can be where f prime of x equals 0, or where f prime of x does not exist, assuming the function exists there. Okay? Assuming the function exists there. If the function doesn't exist there, it's going to be an asymptote or a hole. We'll look at that more later, and we'll talk about that. But that's where you can have critical numbers. I didn't do many of those yesterday, but that's an example of a sharp point. So you can get a critical number from where the numerator in a derivative is 0, or where the denominator is 0, assuming that the function exists there. Okay, we'll come back to some of that later. That's a little bit beyond what I wanted to talk about today, but we'll come back to that later. That's a good thing to remember. Okay. Right, let me go on. Let me go ahead and do one other thing I want to do. I want to add a little more terminology to what we've got here. It won't be a whole lot different, but I want to show you. I want to show you something else here. Let's see. Let me go back here for a second. Take a break while I bring up all this stuff. It's not a very big break, but I want to look at the next section, which really is not very different from this section. And what it talks about is something called extrema and the first derivative test. Now, extrema is just a fancy word for extreme points. And extreme points are what we talk about as things that are maximums, maxes, or what I'll call minimums. Right?
Yeah.
Maxes or mins. So I want you to look at this graph right here. We've been drawing graphs like this, and these were places where there were critical numbers. And if we draw this whole graph, and I ask you, well, let me tell you what a local maximum is. A local maximum is literally a locally high point. It may not be the highest point around, or the biggest dog in the city, but it's the biggest dog in the neighborhood. There are higher points on the graph up here, and there are lower points down here. But if there's a locally high point, we call it a local max. We say there's a local max at that point. So if you look at the definition down here, it says f of c, or y, is a local max if there exists an interval which contains c. So it contains that point right there. So that f of c, the y value there, is bigger than anything around it. And that's what that says. F of c is bigger than or equal to x for all x in between some interval. So the way to think about it really is it's the biggest thing in its area, in its little neighborhood. On the other hand, if I have this low point right here, that's the smallest thing. It may not be the smallest thing in the whole function, but it's the smallest thing in its neighborhood. Okay, we call that a local minimum. I'm gonna leave. Let me get some of this down here. Okay, there we go. So f of c is a local min, or C1 in this case, if there exists an interval around that. So there's if you look at an interval around C1, if you look at all the points in there, f of C1 is the lowest y value. It's called a local minimum. Your book calls these relative maximums and relative minimums. That's just another word for it. I like to use local because I like the analogy of biggest dog in the neighborhood. So there's the biggest dog in the neighborhood right there, the local max. Your book calls it a relative max. They also call this a relative min. Okay, so that's what it is. All right. Guys, as far as taking notes goes, my suggestion for you is to try to sort of write down the definition I'm looking at. I've taken these straight from the book, okay? And hang on, my computer's about to die. I should check things like that out. I can find the end of it. I take them straight from the book. So as far as taking your notes, sort of write down what I'm talking about, and then if you want to, you can go back and sort of fill the definition in as you know. So the mere fact of writing a definition down sort of cements it in your mind. I'm not going to ask you to quote these definitions back to me, but I want you to know what they mean in terms of what we're looking at with the graph. Okay. All right. So let me keep going here. Let's see what I got. So we want to know how we can find these relative maxes and relative mins. It's really easy. We already know how to do it. To find the local extrema, now guys, again, the word extrema just includes local maxes and local mins. They are both extreme points. One's an extremely high point and one's an extremely low point. So local max and min. Local max and min. When they say extrema, they're including both of them. Okay. All right, now, what you're going to do is find the derivative. We have already done that. We know how to do that. There's a function right there. I'm going to use this one. 6x squared minus 6x minus 36. If I pull out a 6, because I know I'm going to need to do it in a minute, I'm going to have x squared minus x minus 6. So I hadn't done anything different. I'm just finding the derivative. The next question is to find the critical numbers. Well, you know what we did to find the critical numbers. We factored this thing. Guys, if you got any problems with factoring, somehow we need to take care of them, okay? Because you got to be able to do it here. I'm going to need a 6 here, and I need a difference of 1. So I'm going to use a 2 and a 3. I need a minus x in the middle, so I'm going to use a minus and a plus. And I don't care what method you use to factor, but that's, if you multiply it back out and you get where you started, you got it right. So tell me what the critical numbers are there, guys. Once I did, this is a plus right here. Once I did this, what are the critical numbers?
-2 and 3.
Perfect. -2 and 3. Okay? -2 and 3. So the next thing I'm going to do is put them on my number line. See, I'm not really doing anything different than I did last night. So that's -2, then that's 3. I'm going to test on either side. And so if I pick a number bigger than 3, up here I'll get, say 4, I'll get a positive, and 6 is positive. I'll get positives. So what that says is it's increasing. Between -2 and 3, say maybe at 0. That's an easy one to check. I'll get 6, 2, and -3. Positive times a negative is going to give me a negative. So that means it's decreasing right there. So in other words, in between there, it's decreasing because I got a negative derivative. If I pick a -2, and make sure you get to where, don't pick -1, it's over here, -3, maybe. It makes this negative, because it'll be -6, -1 times 6. Positive times a negative is a positive. That means it's increasing. Okay, plenty of examples here, guys. I hadn't done anything different. You know what, though? I've got a new word for something I just did. Look at the way these arrows are pointing. This one's pointing up, and that one's pointing down. What do you think's happening at that spot? A local max or a local min? Well, it's going up, and then it comes down. Is that a high point or a low point? It's a high point, isn't it? It's going up and then coming back down. That's got to be a high point. So if you have positive derivatives on the left and negative on the right, you're going to have a local max. And I'll show you how to say it in a minute. Look at the 3. On the left of 3, you had going down, and then you had going up. If it's going down and going up, then what's that got to be? It goes down, it stops going down, and it goes up. It's at its low point. So that's a local min. So if you have a derivative on negative on the left and positive on the right, it's a local min. I like to do it visually. If you write your arrows here, you'll know that's a peak, that's a valley. Okay. I heard a does that make sense?
Yes.
Okay, I thought that was you, Stephanie. So, all right. You remind me of how that sound reminded me of a friend of mine that would do that to me. It's like, I'm not sure about that. So, all right. Okay, so let's keep going a little bit. So what we've got, we say with this picture right here, we say there's a local max at -2. And then we say what it is, we plug it into the function. It is f of -2, and so I'd have to go back and plug it into the function. So if I went back and plugged in -2 here, let's see, I computed this a little earlier. Let's see what I got. I'm gonna compute it. I got 58. I just put it in the calculator, guys. So I got 58 right there when I plugged it into the function. This one we say there's a local min at x equal 3. It is f of 3. And when I plug 3 back into the function, I got -67. Okay? Give me just a couple more minutes, guys. I know I'm running a little bit over time.
And so, you're plugging it back into the original function.
Always.
Right?
That's always what I'm plugging it back into to get points. And so what we've got here, guys, is we've got sort of what we needed. -2 was up here at 58. So I'm going to plot that point. -2 is at 58. Now, let me tell you that the maximum is actually 58. Where it occurs is x. This is the way I want you to say it. there's a local max at the X, it is 58. It's like saying the temperature is highest at 3 o'clock and the temperature is 50. Okay, you've given me the temperature for the max. But it looks like that. If I put in 3 and minus 67, it's down here. And if I look at my increasing and decreasing, what it looked like was something like that. Now, that's a local max. The local max is 58. It happens when you plug in minus 2. Your local min is minus 67. It happens when you plug in minus 3. Now, I'm going to say one more thing because it's going to have an effect on what you do for homework. The only way I can, those are locals. There are such things as absolute maxes and mins, absolute. So, for example, if I went over here to the number 7 and I plugged it in and I got some number bigger than 58, I mean, suppose it's 90. I don't know what it is, guys, but if I plugged it in and I got 90 there, then, and I looked at just, oh, shucks, let me do it again. I'm just going to go right up to it. In other words, I stopped the graph right there. Right, and in this one, I said, I'm going to mess my graph up again, but in this one, I said, suppose I stop my graph at this point right here, and suppose it was minus 325. And again, guys, those points might be fictitious. I got to plug them back in to find that. But if I say to you now, these are the local maxes right here. But what's the absolute max on this closed interval? If that's minus 3 and that goes up to 7, what's the absolute highest value on this interval? Where does it happen? It doesn't happen down here because you got a higher point. What is that higher point? The 790, right? So what we would say there is that the absolute max is 90. What's the absolute min? Well, we got a lower point than that endpoint right there. The absolute min is minus 67. So an absolute might be an endpoint. An absolute max or min might be an endpoint, or it might be one of these locals. So in this case, not only is that a local minimum, but on this interval, it's the absolute lowest thing there is. All right. I'll just say one more word and I'll wrap up. What you want to do here and you'll see it in the book. Anytime they ask you to sort of draw a curve on a closed interval, let's call it, and this one we said, they would say, graph this on minus 3 to 7. You would kind of do your whole graph, and then you would say, oh, I want to stop it here and here at whatever that is, 7 we'll say. I want to stop it here and here and put your endpoints in. Then you can pick the highest point and the lowest point. That's like saying, what's the highest temperature, between 3 o'clock and 2 o'clock? It might be at one of those endpoints, or it might be somewhere else. Okay, the homework, look at the homework. We'll come back and we'll talk about this over the weekend. Make sure you get your quiz in on Monday. And I think I gave you till class time or something on that, but look on Moodle. Again, email me if you've got a question about your grade. I'll be happy to talk to you about it. And then we'll just pick back up where we left off on Monday, and we'll keep sort of working in new things to all of this. Anybody have any questions?
So our quiz is due on Monday?
Yeah, the quiz is due on Monday. The quiz is just on the stuff we did yesterday. Okay, it doesn't have any of this local max, local min stuff on it. Okay, that's the homework, guys. That's the homework there. So just worry about that and get the quiz done. Quiz pretty easy. Okay. Okay. Any question? Anybody? Question for me?
When we do the quiz, are we submitting it the same way that we did the test? Just
yeah, unless watch for an email from me this weekend, okay?
Okay.
Because if I figure out how to do this, you're still gonna email it to me. You're still gonna scan it and email it to me. But if I have to do it printing it again, just make sure when you scan it, you get it sized and you don't have it like, I know you guys were putting it on a black background. That was great, but it left too much black at the top. Just make sure you get get it sized right when you send it to me. That way I won't be, when I pulled the paper out of the printer yesterday, it was like wet with black ink on some of them. Oh man. And I went and bought what's that?
You're gonna post a video of this?
I am. I'm going to post the video of this online. Every lecture, I'm going to do that. Okay, guys? And I'll date it so you'll know what day we were doing things. I haven't quite finished this lecture yet, but I'll get to this. It'll video to wherever I cut off right now. Okay. So watch for emails from me over the weekend. But you're still going to need to scan it and email it to me, because that's the way I'm going to load it into my iPad if I can get it worked out. Okay. All right. Anybody got any questions? Any other questions? Eunice, you got a question? I don't know. You lit up. No, guess not. Okay. All right. Okay. You guys have a good weekend. Stay safe. Stay on board. I don't know if that's possible. Well, maybe it is possible. You got plenty to do, apparently. So I will see you on Monday. Okay.
Thank you. Have a good weekend.
Okay. Bye. Y'all too.